Hey, hello everybody, this is Program 123 again, and today we're gonna see this problem named Multihedgehog, in which the statement, I actually shortened the statement because it's a little bit too long, and it basically says that we are given a tree of size n, and we have to say whether it is a k multi-hedgehog or not. And the constraints are that n is gonna be at most 10 to the power of 5, and k is gonna be at most 10 to the power of 9. Okay. But what is a k multi-hedgehog? Well, let's first define what the hedgehog is, okay? A hedgehog is a graph in which one vertex called center has degree at least 3 and the other vertices have degree 1. Like this one, well, the center is 1 and the other vertices have just degree 1. Only vertex 1 has degree more than 3, which, well, I think what hedgehog is clear, okay? But what is a multi-hedgehog? Well, a k multi-hedgehog is a tree that, starting from its center, all nodes in level I, where I is gonna be between 0 and k, have degree at least 3, and all vertices in level k plus 1 are leaves. For example, the graph that the tree which we see in the image is not a one multi-hedgehog for two reasons. Well, we're gonna get our laser pointer here. Well, it is clear that 1 is its center, okay? But we say that from level 0 to level k, it has to have degree at least 3, okay? So this is level 0, it has degree more than 3, it has degree actually 4. Then for vertex 3 we have a degree of 5, which is more than 3. For vertex 2 we have a degree of 3, well, it's still a hedgehog. And for vertex 4 we have a degree of 2. You may say, well, we have this other edge here. Yeah, but we don't count that, okay? We only count the edges that are not coming from center, okay? And well, this is not a hedgehog because we have a degree of 2 here and we have a degree of 0 here. But I want you to notice this. This is not a multi-hedgehog. This is a multi-hedgehog, okay? So it has to have degree at least 3. For other levels different than 0, it has to be degree 4 or more, okay? Yeah. So that's basically what a multi-hedgehog is. And this problem is kind of difficult to understand at first, but with this explanation that I just gave to you, it's easier to understand it. And the solution becomes quite clear when we see this problem this way. Basically, what we have to see that from center of the tree, we are gonna run a BFS or DFS, what you like, and all those nodes that are at levels from 0 to k, we have to make sure that they have degree at least 3. Okay, not counting the DH that is coming from the center, okay? But the hard thing of this problem is actually, how do I compute? I mean, how do I know the center of the multi-hedgehog? For example, in this graph is actually a multi-hedgehog. We had only two vertices here in 4. Now we have 3. We have another 3 vertices here in 5. So this is a one multi-hedgehog. You see, level 1. Level 0, level 1, and level 2 are all leaves, okay? So that's basically what a multi-hedgehog is. And basically, we just have to find center of the graph and then run a BFS or DFS from center and make sure that all nodes at height between 0 and k have degree more than 3. That's basically what we have to do. But how are we going to compute the center of the multi-hedgehog? That is the big question, okay? We're gonna see. Okay, in order to compute the center of the tree that we are given in the input, there is an important observation. Because this graph should be a multi-hedgehog, the distance between every pair of leaves that do not belong to the same subgraph is going to be the same. I mean, distance from obviously distance from 16 to 17 is going to be 2, and from 16 to 18 I mean distance from leaves that are in another branch according to the center. Okay, so distance from 16 to 7 is gonna be the same as distance from 16 to 9, distance from 16 to 15. So they're all gonna be the same. That's the important observation that we have, and all those paths go through the center. So how do I get the center of the graph? Basically, we just have to run a DFS from any leaf to any other leaf, and well, actually get the longest path. I mean the farthest leaf that we have from this leaf. We know that there are gonna be a lot of candidates, but we care only about one candidate. Okay, so for example, if in our DFS we encounter leaf number 7, then we just have to take the vertex in the middle of the path. Okay, or if we run from 16 to 15, which is gonna be also the same distance, we just have to get the node in the center of the path. Okay. Also, we're gonna see how to do that in code. Well, basically, we start reading our N and K. We initialize our degree array and our parent array, and we initialize our graph, and we assign the degree to every node. And we're gonna call the function center in Spanish, in which we're gonna ask for a vertex of degree 1, which is gonna be a leaf. And well, we push that in our array. In our stack, we are actually simulating a stack with a vector, and we're gonna call an overloaded function of this center. Okay, an overloaded version of this function center, and we're gonna establish our greatest distance to 0 and our current number of nodes to 1. This is what variable d does. Okay, so basically in our overloaded function center, what we're going to do is that we're gonna push first our element in the stack that we have, and now we augment the number of nodes that we have seen, and whenever this becomes greater than our greatest variable, well, we assign accordingly, and we take the node in the middle of the path that we are computing. Okay, and then we just do our DFS. We reduce our current number of nodes because we are going back in our recursion, and we take out that element from our stack. So that's basically what we have to do to get the center, and this variable c is the center. Okay, so after we get the center, we're gonna have a global variable named band, which is gonna be like optimistic. This graph is gonna be a multi-hedgehog, a k multi-hedgehog, until it's proved wrong. Okay, we call a DFS function, and we have to reset our array of parents because we used this in our central function, and we're gonna use it again in our DFS. Okay, and well, we reset this, and we are gonna run a DFS from center to all the leaves to see if we fulfill the condition, okay? Well, what do we do in our DFS? Well, if our height is less than k, then we have to ask if the degree of this vertex is less than 3. And look at this. When we go farther in our recursion, we are gonna reduce the degree of our next vertex. Why? Well, because we don't wanna count the vertex, the edge that comes from center, and that's why I am decreasing by 1 the value of the degree, okay? And if edge is equal k, then we just have to make sure that our degree, the degree of the leaf, is 0, because we are not counting the edge that comes from the center, which is the only one in a leaf, okay? And we increase our height variable, and then we decrease it. That's it. That's everything we have to do to solve this problem, and it actually gets accepted. And that's everything for today, you guys. I hope you enjoyed this video. I hope this video was useful for you. Remember to share with those who need it, and see you in another video. Bye bye.